Hi, so as the last thing between you and lunch, I will try to make this quick. I'm here to talk about our progress towards developing global quantum entanglement networks. So we last time talked about what kinds of things need to happen to demonstrate a global quantum entanglement network, and our first step, which we announced last year, is that we are launching Q4S, an entanglement swapping satellite. But I need to back up and talk about what we've already done in order to talk about what we're going to go do. So that source looks a little bit like this. We've worked very closely with NASA and with researchers at the University of Illinois Urbana-Champaign. In fact, many of those are here today. I urge you to go to work at, do the lab escape up on the third floor balcony. That is the team that actually built SEEK, which you see there. You see that there on the International Space Station. That was the US's first quantum networking experiment that was fielded into space. It is an entanglement source that actually has demonstrated that they violate Bell's inequality by their number is somewhere north of 2.5, 2.6-ish. So a great example there. We're going to launch Q4S next year. And then we're already planning what are the next things that we have to do. Once we demonstrate entanglement swapping, we actually have to demonstrate an entanglement link, and then we have to link multiples of these together. So that's the journey that we're on, the big picture of what we have to go do. All right, SEEK was started in 2021, launched in 2024, was built as a PhD thesis of 2 graduate students in Paul Kwiat's lab. The guise of this was to demonstrate an entanglement source and to show that they could overcome radiation damage using annealing techniques in the nonlinear crystal. They've done this. They flew, and that launch you see there, the beautiful picture was taken by Liam of the launch of this experiment in November of 2024, and they had first light shortly after that launch. And as of July, they'd completed all mission objectives, again, demonstrating violation of Bell's inequality to better than 2.6. So now our Q4S mission will launch next year. We talked about this again last year. Our goal is to not just demonstrate that we can produce entanglement, but that we can demonstrate the protocol of entanglement swapping, which is really a four-photon quantum effect, and we want to use that demonstration to evaluate components that are needed to do this. So let me remind you what this protocol is. So we start off with a laser source that is going to pump 2 nonlinear crystals, and the point of that is to create 2 pairs of entangled photons. Again, I said this is a 4-photon protocol. We're going to expend 2 of these photons by selecting those and sending those into a Bell inequality measurement system. And when we measure that correctly, we will be able to demonstrate that that central pair is entangled with each other. So in entangling those 2 photons, we've now entangled all 4 photons because, again, the 2 pairs that came in were entangled. Therefore, we now have all 4 photons entangled. Those 2 are spent in order that the other 2 photons may be transferred to other locations in a network. Again, the remaining photons are now entangled, and we have those available as a resource to use. So building an experiment to do that has been something that has been done over time, many times over. And it really comes down to, once you understand the concept, you have to actually understand how you trade off the component characteristics that you need. So we're going to walk you through what it's like to go from this concept through a lab experiment to get ready for launching in space. It's not quite the same as doing work in the lab. And so let me highlight a little of those differences for you. So in looking at a trade study, well, the first thing you have to ask is, how is it I'm going to generally accomplish the task? And in our case, again, we have a nonlinear crystal. We have to do some timing compensation, some spectral filtering to make sure all these photons that are going into this system, those pairs of photons are correct, or are the same. Then we have to send those photons into a polarizing beam splitter that sends one photon one direction, one photon the other direction. The photon that passes into that green Bell state measurement box, that pair is the ones that we're going to check for entanglement, and therefore entangle the photons that are at the transmit or receive part of the essentially what would be the communication nodes of Alice and Bob. Then we measure all of the combinations of what we see and validate that this works. But the trade comes down to understanding, doing this in a lab, I don't have to worry about a lot of things. I have to figure out how I make this work fast, but I have almost an infinite amount of power I can expend in doing this, whereas in a satellite, that's entirely not the case. So I have to think about, how does my swap rate scale with these things? And it turns out the swap rate scales basically by how well I can create my pairs. The better I can do that, the better off I'm going to be, and by how well I can detect my photons. So because I have to detect 4 photons, that detection efficiency is raised to the 4th power. So I'm really penalized if I spend a lot of power on detection efficiency to raise that efficiency up even a little bit. So what this ended up forcing us to do is to change the wavelength, to sacrifice a tiny bit of detection efficiency for a lot of power efficiency, and put more efficiency into the biphoton pulse, biphoton pair creation. So this is how we worked out what the lab system would look like. So now we build a benchtop system to take this overall model, validate that this trade works out, and that we'll get the performance that we need. And we showed these results before. We understand how to do this. We get good fidelity. We're actually showing that we can extract the information that we want to do over long periods of time. This is the data you see on the right-hand side there is a little more than a day's worth of data. So we've done the end-to-end measurements in the laboratory, show that everything works. We've set requirements then for what we have to do. We've then engineered and designed a payload. That payload then now has to meet the constraints that we have of the satellite that we're going to put this in, which really comes down to be very extreme. We have less than 12 liters of volume to work with. We delivered a payload design concept under 10. We had 21 kilograms of mass that we could work with. We delivered a payload design that is 19 kilowatts. We had about 50 watts of power available. We're at 45 watts design power draw. We want that to produce over 100 swaps an hour at a high fidelity. So now we have to go build the subcomponents and the assemblies that take that payload design and turn it into something real. And that picture you see on the right-hand side there is a photo of our ground twin assembly. This is everything that will go, exactly the same as everything that will go into space, but is the non-space hardware, the non-flight hardware. So we're going to go take that system, and then we're going to go put it through environmental testing. And by environmental testing, I mean we put it into a vacuum chamber and we expose it to the thermal environment that we would see on orbit. And just to give you a sense of how fun this is, when you're in a lab and you're trying to do this experiment, you're dealing with laboratory temperatures that change maybe a degree or 2 a day. When you're in orbit, you're dealing with temperatures that change between 10 and 20 degrees every 90 minutes. So we have to show that we have a system that is robust and can handle those large excursions. And one good way to check this is to make sure that we get visibility of our entanglement over long periods of time, but also show that we can track and maintain pointing stability as that payload assembly flexes and thermally expands and contracts due to those temperature changes and those rapid temperature changes. And what you see there, those are clouds of pointing taken over 80 hours of data while in an environmental changing, undergoing large temperature swings. We also look at, do we get the timing that we need? Do our photon pairs come in exactly when they need to? That tells us, again, has the payload expanded or contracted? That means that these things don't arrive at the same time. If they don't arrive at the same time, they can't be distinguished as identical photons coming from the same pair. And again, we have to show that in the process of measuring tomography, we can control the beam and make sure that within our range of beam control that we can maintain the fidelity and keep the sweet spot of fidelity within the range of that beam pointing system. Again, all of these are measurements that we do as we are characterizing this entire assembly that is now proving out what we need to go do in flight. Now, I don't have graphical form of data because it's hot off the presses, but I am able to say that we have taken this system and successfully shown the generation of the four-fold entanglement that we need to see on orbit to do our mission and we just did this over the last weekend, so this is why I don't have the ability to show this today. Which means we are exactly where we expected to be because we are in the process of doing our final assembly build for the flight hardware, which will be delivered to our satellite payload and perform our on-orbit demonstration next year when we launch. So again, building something for the field is very different than building something for the lab, and it is really a powerful thing to do as a team to demonstrate that you both understand the science, you understand the mission that you want to go execute, and you understand, therefore, the engineering that has to bring these two things together and can pull all of this together in a coherent, integrated way. Now, all this is very exciting, and I am incredibly proud of our team for the accomplishments that we have done to date and will continue to do as we launch Q4S. But that's not enough. We want to think about where do we go from here. As we said, the journey is not launch seek, demonstrate entanglement, launch Q4S, demonstrate entanglement swapping, and then stop. We need to look forward to how we show that we can generate entanglement links and how we can develop and generate entanglement networks. And so we have actively been studying, determining what kind of fundamental mission considerations. Well, we've looked at where all the conditions are for mission that lay out how you would conduct the kinds of missions that we're talking about, which really come down to you can have an uplink, downlink, a symmetric uplink, downlink. You can have a double uplink. In other words, you can have a ground station that talks to two different satellites and it distributes your entanglement that way. Uplink, downlink, you would have your entanglement source on the ground, one in space. Your double downlink, you start your 4-photon production in space and you send 2 of them to the ground. And you then compare later. You have a crosslink where you have 2 satellites and you have your entanglement sources split between the satellites. You demonstrate that you can link across those. And you have your generalized end-to-end link. Oh good, it's showing up better there than it is down here. Where you cross over and you have something that's closer to a full network demonstration. We have been looking at all of these configurations. We've been looking at doing studies that balance what is the mission capability that we need to produce, what is the technical risk associated with doing that, what's the schedule that we could maintain to get that done, what's the cost of doing that, so that we can assess and figure out what our next step will be, what makes the most sense and balances all of those things to bite off the biggest chunk of capability at the most reasonable technical risk that we can execute as quickly and cost efficiently as we possibly can. And that has been the focus of our team in the end, from the start, has been on that long-term objective. And that long-term objective is building a global entanglement network. And by that, we mean one that spans national borders and enables us to use these resources for science or for other public goods, and in so doing, establish a capability that the world can benefit from. We've been interested in that as a company from the time that communication networks were developed. We'll be interested in that until we can show that this is able to be done and executed. With that, I thank you for your time. And as I said, we're looking forward towards building those future global quantum networks, and I will come back and talk to you about them as we've done that.